Um, Hello, everyone, and thanks for coming to my presentation, and thanks for the organizer to inviting me. It's a pleasure to be here. It's my first time in Moscow, so it's as cold as I was expecting. It's actually very similar to Montreal anyway, so it was not so bad. So I'll try to give you a presentation about a few things I've been doing in the last year or so. It's just a few random things, and the overall topic is how to handle structured data using deep network, deep architectures. And of course, what I'm going to talk about is not my own work only. It's a collaboration with many people in the Google Brain team where I work. So let me start with trying to explain you what I mean by structured prediction, which is one of the topics I'm going to address. So in the structured prediction problem, you have some data, and you're given some input, X, and you have to produce some output, Y. And X can be anything. In that case, it's an image. But Y is a structured object. It's not just a yes or no, 1 or 0. It's a set of decisions. Here it's a set of pixels that you have to provide. And you have to provide, in that case, for a semantic segmentation of images, you have to say whether it's like the motorbike or the human or the background. And each of the decisions, each of the pixels are related to the other decisions. So that's why it's structured. It's not a set of independent decisions. They're all together forming a global decision. So that's what we call structured prediction. There are other tasks that are structured prediction. For instance, a sequence task like speech recognition or machine translation, where you have some input. Here, X is a sequence for machine translation, and the output, Y, is another sequence of words. In that case, it's the translation in French of a sentence that is in English. And again, we have that it's not just that you have to decide each of the words, but it's more that the whole set of words are organized as a sequence, has a single meaning. So it's very structured. As I am saying in the slide, it's multivariate. There are multiple options. All the decisions are correlated. It's also constrained. You cannot say invalid sequences. And each of the decisions is discrete. So this is the set of problems that I will call structured prediction. Another example of that is image captioning, where you have an image and you have to provide a caption that explains what the image is. And in fact, I'm going to go into more detail about image captioning. Here I give an example of the task where you have this baby in that image, and we are given a training set of such images where some humans have actually annotated the images by giving a sentence. And here I give an example, a young girl asleep on the sofa cuddling a stuffed bear. That describes well the image. Now we are going to train a model that tried to do the same thing. So we trained the model, and we called it NIC for Neural Image Captioning. And it was producing sentences, and here I give two examples. So one thing I want to mention when it produces these sentences, the first thing is that the sentences are very different from the one human provided. But it actually describes the image. They are valid English sentences that describe the image, and every time you ask for a sentence given the same image, you get different output, all of which describe properly the image in various ways. So when we trained that model, and I'm going to talk about how we did that in the first part of the talk, we were really surprised that every time we would use the model to try to describe an image, it would produce a sentence that was valid, and not always, but sometimes actually describing the image. So let me start back by the much simpler task of image classification. So in image classification, you are given an image. Here there's this bear, and the task is to decide what's in the image. So you have to classify among a fixed set of classes. Here, is it a cat? Is it a bear? Is it a plane? Whatever. And that task has been tackled by computer vision scientists for decades. And there's a lot of data set that people use, and one of them is called ImageNet. It's been available in the last 7 or 8 years. And over the years, the way people used to try to solve that task was by separating the task into two type of subtasks. The first one was to extract features. So you would use computer vision experts would look at the image and say, well, we should count the number of red pixels. So that would be a feature. Or we should count the number of lines that are like this and lines that are like that. And there was a lot of knowledge about what kind of features we could extract from images that could be used to then try to decide what's in an image. Once you had a good set of features, you would use a simple machine learning model, often a linear model like an SVM, a support vector machine, which was very popular in the 2000s, to try to classify the model by training usually one model per class. So you would train a model that says, is it a bear? Is it a bear? Then is it a cat or not? Is it a fly? Is it a plane? Whatever. So that's how it was working until about 2012, where things changed dramatically when at last neural network, or deep learning as it became to be known, started working much better than the classical view. Note that machine learning using deep learning or neural networks have been there forever, but for some reason it was not working as well up until 2012. So what happened in 2012, there's this architecture that I'm showing you here, which is quite complex, that was used to train a model on this ImageNet data, and that won the competition by a very, very large margin. So compared to all the previous approaches, it was significantly better, and everybody was amazed and tried to understand what was going on. Roughly what this architecture is, I'm not going to go into details about what it is, but it is starting from the pixels instead of starting from features. So we remove all these human knowledge of feature extraction, and we go directly to the pixels, and then we apply a sequence of nonlinear transformations, some of which are called convolutions, max pooling, dense connection. There are multiple types of nonlinear transformation you can apply. And at the end of this series of nonlinear transformation, you get to the end of the model, which would be this last layer. So the image was at the beginning here, then it goes through multiple layers of transformation, and at the end you have a last layer of the decisions. Here it was a 1,000 class problem, so there was 1,000 numbers, each of which was associated with the probability that the image contains a bear, a cat, a dog, or whatever. And you would train this whole model in one go with a gradient descent approach, so something that we have been doing with neural nets forever. But this was done from the pixel to the decision in a single architecture, and with the size of the available data set and the amount of computing power that was now available in 2012, plus a few tricks, which I won't go into details like dropout, it started working very well, and that was basically the beginning of the era of deep learning that works. Actually, these kind of architecture have been evolving through the years. One example from last year is what we called Google Lenet, which was a model proposed by Google to try to win the challenge of the same ImageNet challenge that happened every year. And so this strange model, which looked like a snake, had about 20 layers, each of which doing different things from the image to the decision. And that's actually not the one who won. There's another one that won that's called ResNet, and I won't go into details, but it had up to 150 layers. So you see that these models are becoming bigger and bigger, but they're all trained in the same way by stochastic gradient descent with various tricks to control a lot of details, but I won't go into detail, just to know that research have gone through many steps for computer vision, and now we get these models that are actually better than humans for this task. So that's all good, but that's only one part of the story for image captioning. The second part is to be able to produce sentences. And sentences start with words. So we need to be able to have a meaningful representation of words and then sentences. So let's start with words. The usual way to represent discrete features like word would be to decide on a vocabulary. Say we are going to have 1,000 words, 100,000 words, and we are going to create a vector that represents these words by saying, by using what we call the one-hot encoding, where each word would have a code which would be composed of only zeros except one value that would be a 1. So Obama would be 1 followed by 0, 0, 0, 0, 0. Dolphin would be 0, 1, 0, 0, 0, 0. Berlin would be 0, 0, 1, etc. So that's good and that's easy to create such a vector, but the problem is that this representation doesn't say anything about the meaning of the word. So in that representation, Obama and Dolphin would be as far away from each other than Berlin and Paris, for instance, which is not a very good representation. So an alternative to that would be to put the words inside this hypercube. So instead of being at the extreme, you would put them inside, and hopefully in such a way that two words that are nearby would actually have similar meanings. So I'm illustrating that here by showing that Dolphin and SeaWorld are related to each other, so they're not far. And Paris and Berlin are also related to each other, so they're not far, but Obama is far from both of them. Now the question is, how do we find this representation? One thing I should mention about another good point about this representation is that the number of points you can fit in that hypercube does not relate to the number of dimensions of the hypercube. In this representation, you needed to have a number of dimensions that was dependent on the number of words of your vocabulary. Here, you can put as many words as you want and still have a fixed dimension that could have other reasons for its size. So how do you find these points in this hypercube? Well, people have been working on that actually for many years. I'm sure I don't have the whole literature on that, but I know that in the early 2000s already, people like my brother was training models where the first layer was embedding of words. It was not for this task, but it was for a language model task, but it gave about the same performance. Nowadays, we have much more efficient way to train these models, much simpler. So one of them, for instance, Word2Vec is super efficient. You can train your model very quickly, and it's totally unsupervised. The only thing you have to do is pick a corpus of text, say Wikipedia, for instance. You take all the words in Wikipedia, all the documents that are in Wikipedia, and then the training is as follows. You decide on the dimension. So, for instance, each word embedding will have 100 dimensions. You initialize randomly all these word embeddings, so they are all over the place. And then you randomly pick one word in your corpus and one word nearby the other one. So basically, randomly pick two words that are nearby, and then you just move the two embeddings that you picked nearby each other. So the fact that they were nearby in the corpus probably means that they are nearby in the semantic sense. There are reasons for this to happen, and that's the only thing you do. Now, there are other techniques, like if you can also take a third word that would be far away, and you try to push them away. But to simplify, there's this very simple algorithm that is stochastic. You just pick random words, you modify slightly the embeddings, and at the end you find something very interesting. So once after you've trained after like a few hours, and even less now, you can pick a random word in your corpus, and here, for instance, let's take the word car, and you can look in this new embedding space that you created, what are the nearest other words, and what you are going to see is words that are related to car. So cars, muscle car, whatever that is, sports car, etc. Car type of things. Or near tiger sharks, you're going to find these other words. So without telling the model that a shark is similar to a tiger shark, or that car is similar to cars, just by assuming that words that are nearby in the text will be nearby in the embedding space, you get to have this representation. So that was very surprising that we could just do that easily. The graph that I show here is to show that all these green dots here in the embedding space were all about the same semantic. They were all animals. All these blue ones were all, what is it, dogs, etc. So naturally, without telling them all about how related the words are, just by training with this very simple trick, words that have similar meaning went next to each other in this embedding space. Actually, there's even more interesting properties that first when they appeared were really very surprising, but now we start to understand what's going on. It's this idea of that I'm trying that you can do some simple arithmetic with the word embedding. So for instance, and I give an example here, if you take the embedding of the word Rome and you subtract in the embedding space the vector representing the word Italy, then you add the word Germany, you get to a point where the nearest point that you will see in the embedding space is going to be Berlin. So in other words, Rome is to Italy what Berlin is to Germany. And we never had to provide this kind of information. It was found naturally. So this means that the embedding space really captures something fundamentally important in the words and their meaning. So that's all good. But what about sequences of words? So now we know how to represent words, and that's a good step towards doing image captioning, but we actually want to have sequences. So what do we do with sequences? Well, a sequence is just a sequence of words is a set of events that you want to happen together. So for instance, you can try to model the joint probability of many things. So here I'm calling that here P of Y1, Y2 up until YT. I want to try to be able to estimate the probability of a sequence of words happening one after the other. Turns out that this joint probability can be factorized without loss of generality by the product of the probability of each word given all the previous ones. That's easy so far. And for many years, people have been just doing this by cutting the last words, so saying I'm going to represent that by just keeping the last 3 words, for instance. So that would be 3 gram or 4 gram. Instead, of course, because neural nets were starting to work well, we started to use a flavor of our neural nets called recurrent neural nets, where we are going to represent the past, all these words, by just a state vector. This here is ht. And that state vector itself would be a function of the state vector at the previous time step. So I'm trying to unroll this to show you what's going on. So in order to represent the P of YT given the previous Y, it's going to be represented by this blue, it works here, yeah. Okay, this blue box here that represents P of Y2 given H1, and we see it by going back here. If we look at the last one, P of Y4 given H3, actually, so P of Y4 depends on Y3, then it depends on Y2, and it also depends on Y1. So all the relationships are kept in the model through the recursion over the hidden state. So that's a recurrent net, and if you train it with putting parameters at the right place in F and in the softmax box, you are able to actually maximize the likelihood of these joint models, joint probability models, and you get quite good performance. So that's a way to compute the probability that a sequence of words can appear in some corpus that you are given. That's a good step towards doing what we want, but that's, again, not enough. There was one more step missing, and that's the sequence-to-sequence framework, which was proposed about a bit more than 2 years ago, actually 3 years ago. And the sequence-to-sequence framework was saying, well, we have these recurrent nets that can be used to read sequences or to evaluate the probability of a sequence. But what about problems where you have an input sequence and you want to map it to an output sequence? And actually, the task they had in mind was machine translation, where you have a sequence of text in English and you want to translate it into a sequence of text in French. So you have these 2 sequences. They have different sizes. Here I represented by T prime and T. And you want to basically try to maximize the probability of generating the French sentence, no, the English sentence, given the French sentence. So again, you can use the same trick as we use for language model and just decompose this into the probability of each of the English sentence word given the previous English sentence word and all the French sentence words. And now you need a model to represent that. And that's the idea of this sequence-to-sequence model, where you are going to concatenate two recurrent nets. One that will read words, and that's this green sequence here. So you read all the words. They go into this state machine that accumulates a representation of 1 word, 2 words, 3 words, 4 words. Once you've read all the words, and you represent that by a special symbol, here it's this dash, that says, I've read all the French words, now it's time to produce English words. And now you have a second recurrent net that will produce English words 1 word at a time. So it's going to produce Y1. And now given Y1, it will produce Y2. Given Y2, it will produce Y3, etc. until it produces a symbol that is that means end of sentence, and it means we're done. We have generated the whole English sentence. So you can train this model again using a classical model for language modeling with a few tricks, and I'm not going to go now into details about that. I'll go back to it, the tricks that can be used to make that work. But suffice to say that this is a good way to represent sequences or transformation of sequences to other sequences. So and now it's time to get back to image captioning. In fact, if you think of image captioning, you can see it through the lens of machine translation. In machine translation, we were trying to produce an English sequence given a French sequence. And now we're going to try to produce an English sequence given an image. Now we know how to represent an image. We have all these very complex convolution network that I've talked about. And we know how to represent, to generate sequences. So let's put together these two things. And that's basically the architecture of the image captioning model, where we just stitched together these two techniques. One, which was you take an image, you pass it through your best convolution net image model that you have so far. Here it was this Google net I talked about. And the last layer of the Google net, right before it takes decision, is put as input to this recurrent net that will try to produce a sentence. And you train it to maximize the probability of generating the right sentence given the image that is given. And now it's just a matter of training the model and trying it. So it turned out that in 2014, there's this data set that came out, which was produced by Microsoft. So they called it Microsoft Coco. And it was like one of the biggest at that time data set that contained images and sentences. Actually, each image had up to 5 different captions. So when we saw this data set, we said, okay, it's time to try that. We have a big enough data set to try this kind of task. And so we just stitched this Google net. We connected it with this recurrent net called LSTM. I'm not going to go into details, but that's the flavor. It's one of the flavors of recurrent nets that actually work well. And we decided on a dictionary of words that could be used to generate these sentences, a very small dictionary, about less than 10,000 words. So you can say a lot of things with 10,000 words, enough at least for this kind of data. And we just trained the model. And here are examples that came out of the model after we've trained. So now these are examples from the test set. So these are images and sentences that we've never seen before, but it gives a flavor of what's going on. So you have this image, and you have the human translation here, and we have Nick is trying to explain what it is, a man feeding a giraffe at the zoo. So it's not perfect, because in fact I think there's a woman as well, and Nick doesn't see the woman. Okay, but it produces a valid sentence, and for that we were very happy. Then, well, I don't understand how the images are not. The quality of the image has disappeared. Anyway, there was a sign here, and well, it was supposed to be, I forgot, a stop sign. We don't see it now, but it's working anyway. You have so a brown dog laying in a red wicker bed. A small dog is sitting on a chair. Very similar, but then it doesn't always work. That was the main purpose. we tried it on an image of our own, and I suppose you all know about this, this dress that some of you see as blue and black, and some of you see as white and gold. I personally see it as white and gold, and Nick didn't see any of the two. It saw a close-up of a vase with flowers. So I think this was to illustrate the fact that you might have seen a lot of these successes, but there's a lot of failure as well. And images in the wild are harder than images in a training set, so this is you have to understand the limits of these approaches. One of the, I mean, there are many limits for this, but one of the limitations is that generating valid sequences of words is actually a hard problem. What we thought was hard was to generate sequences of valid sequences of words that would be actual English. Turned out that this was actually easy. What was hard is that the images, the sequence actually described the image, like in this case. So we've continued working on sequence problems because we think there's more to learn about that. And recently we've tried to add some ideas from reinforcement learning to our problems that involve producing sequences. And I want to talk about one such idea that we've just presented last week at NIPS in Barcelona. So there's a lot of people involved in this, but it's mostly the first author and the last author that did everything. In the middle, it's us. Let's start with this idea of a reward. So in machine learning, we have such a thing called the loss, which is what we are trying to optimize, minimize. And then we have another thing called the reward, which is what we really want to do. So for instance, in classification, the reward will be how different is what you want from what you got. And in classification, either you got it or not, so it's 0 or 1 reward. In segmentation, the task of the beginning with the motorbike and the person, you want all the pixels to be right, so there's this thing called intersection over union, where you compute how many pixels were common between the correct and the obtained segmentation divided by the union of both of them. In speech recognition, there's such a thing called word error rate, which is a version of the edit distance, where you want to see how many words are in common, how many insertions you had to do, or deletions. In machine translation, there's another thing called bleu, where you are counting how many unigram, bigram, trigram, and fourgram are in common between the obtained sentence and the target sentence. So all these are reward functions, and that's usually what you really want to optimize, or proxies of what you really want to optimize. But that's not what we are optimizing. So what are we actually optimizing? In general, we are given a training set, a data set of pairs, input-output, so that's which I called here X and Y, and we are given N of them. And what we are going to do in general is to maximize the probability of generating a Y given an X. That's what we were doing with this sequence-to-sequence model, or with maximum likelihood over language model. This is usually what people do, because we know how to do that. There's a sound approach to do it. We want to do that, but the way we are going to use the model after it's trained is by trying to find the best Y given an X. So we're going to give the model an X, and we're going to try to look for the best Y, the one that maximizes the likelihood for this X, and this is the Y we want to produce. Now, of course, it's impossible to find that this argmax is over a combinatorial number of possible sequences of words, so you have to use tricks like beam search to try to find among a reasonable set what is the best one. And again, even though you have this first trick here, but you have another problem, which is that you actually don't care usually about the maximum likelihood. What you care is this reward. So you hope that by training likelihood and doing this argmax with a beam search, you will maximize the reward. So there's a lot of hope here. Whether it's going to work or not is not clear. So how do we do that? So I talked about this, the chain rule that you are going to use to factorize the probability of Y given X as the product of the Y's. And this has a lot of nice properties. In particular, it's easy to implement with the sequence-to-sequence model. So that's just another view of the same graph I showed you before. That's all good, and we know how to train that. Now, the problem is that what we really want, again, is not to maximize the likelihood, but it's instead to try to maximize the reward. But the reward is hard to optimize because when you change slightly the parameter set, so the parameters of your model, it might not change for a while. So that's what I'm trying to illustrate here. You change the parameters and nothing changed because you still produce the same word. Then you change it and then suddenly, poof, you're producing another word because now you're slightly different in the embedding space and you get a different reward. So your reward compared to when you change the parameters is not smooth. So it's very hard to optimize. So that's sad. So instead, as I said, people just use maximum likelihood and hope that this will improve their reward. So the problem is that you need a lot of hope because there's nothing in the loss that you're optimizing that talks about reward. You're just maximizing the likelihood, and you're not telling the model. So when you maximize the likelihood of the target sentence, you're basically saying, well, this is the target sentence, and that's the right solution. Please maximize it. And any other sentence is wrong. So that's what I'm trying to illustrate here. You put all your eggs on this target sentence, and you say anything else is wrong. Now, the bad thing is that you're saying anything else is wrong, no matter what it is. You might have only one word that is wrong, or you might have 10 words that are wrong. All of them are wrong equivalently. It doesn't capture this thing that some wrong are less or more wrong than other wrongs. And that's what the reward is telling us, but it's not there. So people have been trying to add some notion of reward in their approaches. One of them is this mixer approach from Ranzato et al. From the Facebook team, where they did the following. So they say, okay, we're going to take our model, our current model, and we are going to sample. So we're giving an X to the model, so we're giving an input, and we're asking the model, please give me the best sentence you think the model think it should be. And you get this Y, and you attribute a reward. So what you do is you have your model, you ask the model what is the model thinking of the correct solution. The model gives a solution, and then you tell the model, well, this was wrong, and here is how wrong it is. There's a reward or how good it is. And given the reward, now you use some reinforcement learning algorithm called reinforce to try to propagate the reward to the parameters and improve the model accordingly. So you are asking the model to provide a solution. It provides a bad solution, and you try to tell the model how to improve. So in theory, that sounds like a good idea. In practice, it's a good idea because now you actually have the reward inside the loss function. In practice, there's a big problem. In particular, when you start, you're asking the model to provide a sentence. The model is random at the beginning. There's nothing in the model. So you're asking a sentence. It's going to produce garbage. So garbage will then be rated, and the reward will be 0 because it's just like a random sentence. So there's no reward, and if there's no reward, there's no gradient, and you cannot improve from nothing. You can only improve if there's something in the signal. So it's very hard to train, and usually people, in order to train that, they first train a maximum likelihood model, and from that model, they go back to this approach, and then they try. So there's like multiple steps involved with some scheduling that is hard to tune, but still, it works better than this. So it was a step in the right direction, but not good enough for us. So we went to this approach that we called reward augmented maximum likelihood. In this approach, we actually do something slightly differently. Instead of sampling from the model and then scoring with a reward function, we're going to do the other way around. We're going to sample from the reward function and scoring according to the model. So what do I mean by that? I mean, let's suppose you have this function here that I call Q, which is represented here by an exponential function around the correct solution. So imagine you have this reward y star is how good y is compared to y star. And you are going to sample sentences that are not far from the correct solution. So imagine this distribution of sentences centered at the correct sentence. So the correct sentence gets the highest reward. And if you sample according to this Q distribution, you sample more often the highest probability sentence, so the one that has the highest reward. And depending on this hyperparameter tau, you'll have more or less, so either peaky or very flat distribution around the correct one. You'll have a probability more or less big to sample a sentence that has lower reward. So you're basically sampling sentences according to the reward distribution. So a few examples that I'm showing here. If tau is 0, it's actually the same as the maximum likelihood. You always sample the correct sequence. So basically, you always sample y star. But as soon as tau grows, you will sample other things. Now, once you have sampled these sentences, you are going to tell the model, please maximize the likelihood of this sampled sentence as if it was the correct sentence. So now we're maximizing the likelihood of a wrong sentence. But it's wrong, the model doesn't know it's wrong. It's wrong according to the reward. It has higher probability reward will get more chance of being sampled. So the model trains by jointly learning to maximize the likelihood, but also by learning what it means to make a mistake, because it's embedded into this Q function. So it learns what is a reward. And we think that is good because now there's a reward. It knows how to train to maximize the reward. But we are still using the real label because the sentences that are sampled depend on the real label. They do not depend on the model, which could be wrong. They depend on the label, which are always right, or so we think. And more or less, it's actually very easy to train the model because you can just use gradient descent. So you just sample this wrong sentence. There's a question in the back. Here. Here. Well, so it was just to illustrate the fact that the distribution itself can be multimodal, the distribution over the correct. There are multiple ways to make mistakes, and when you sample some of them, you may have a small. This is the x. The x-axis is the parameter space, and as I said, it's not at all unique or continuous in the parameter space. It could be very different. But what matters is that you explore the parameter space appropriately, and it could be multimodal. There's nothing that says that it shouldn't be. It's not the reward that we see here. It's the parameter space. And as we said earlier, it's very discontinuous function. So it's very easy to train this model because it's just maximum likelihood over a different set of sentences and not the true ones. But once you've selected the sentences according to the Q function, it's just maximum likelihood over them, nothing else. So now there's one thing I haven't talked about is how do you actually sample from such a distribution? Well, it depends now on your reward. So let's talk about the simplest reward, which would be the Hamming distance. So suppose that you have sentences of size n, and you are going to only consider sampling other sentences of size n. So that's a very simplified setting from, say, word error rate or bleu. But it's a first step towards them. So it's actually very easy to sample other sentences of size n if you have a fixed dictionary, because you can easily count for each other sentences of size n how far they are, so how many differences they have with the correct sentence, and hence you can actually count the total frequency, the total number of sentences you could generate. You have a fixed dictionary, so it's just going to be these numbers. It doesn't really matter. But because of that, you can easily use a multi-step process to sample first how many distances do you want to have, k of them. You can easily compute what's the probability, the prior probability of sampling a sentence with k mistakes. And once you've decided on the k mistakes, you can just now select these k mistakes randomly and select another word according to them. So it's actually very easy. going from Hamming to edit is a bit more involving, and it requires a few tricks to account for insertions and deletions, and that's feasible. Going to more complex distribution like bleu is actually much more hard, and we don't have very good solutions for that, but you can always use importance sampling. That is, you sample from Hamming, and then you correct for the fact that it's not exactly the same as Hamming, and one can do that. It's just a bit longer. So what is important here is that even though it might be involving to sample from that distribution, you can always do that a priori on your training set way before you train. You can save all these new sequences you're going to train on in a separate training set that you're going to keep instead of doing that on the fly. So with Hamming distance, you can do it on the fly because it's very efficient. But maybe for more involving distribution, you might do it prior somewhere with other machines somewhere else, and then you can use them during training. So let's quickly go over a few experiments. Two sets of experiments, one on speech and one on machine translation. So for speech, we use the timid dataset, which is the equivalent of the MNIST dataset for images. That is, it's a very small benchmark that people have been using over the years, which remains interesting to understand new experiments. But of course, when you actually want to do real speech, you should not use that. But it's good to try things. So I'm describing here the model. It's not important. It's a sequence-to-sequence model with attention, and we train the model to produce the sequence of phonemes given the audio. What matters are the results. So we're comparing here with the plain maximum likelihood solution. So here we give result on the dev set and the test set. What matters is the test set again. And in that case, we're talking about phone error rate, which means the lower the better. So now what we have this tau parameter, which represents how much noise you want to put in when you actually sample the examples, so the target. And so we varied a bit this tau to see what was going on. And what we see is that the performance improves up until some number, and then it starts to deteriorate. So the first good point is that at the optimal on the dev set, the test set gets the best performance. It's very smooth, so it's not like totally unstable. I think one more interesting thing to say is that the optimal was at here tau equal 0.9. So let's look at what it means to have tau equal 0.9. We actually computed how many mistakes we've put in the model by having a tau equal 0.9. So by first looking at tau equal 0.6, this graph should say that about 60% of the training set had 0 error added. And then there's another 25% that had 1 error added, etc. Now with tau equal 0.9, all sentences were wrong. So they were all sampled with at least one mistake, or almost all. Let's say 99% of them had at least one mistake in the training set. So the model basically trained with wrong sentences from the beginning, and only wrong sentences, more or less wrong. So some portion of it had 7, 8, or 9 mistakes in the same set of 20 symbols. But nevertheless, having been trained on all wrong sentences, it actually produces better right sentences than the ones trained only on correct sentences. So what about machine translation? Well, so machine translation, again, it's a very similar model, sequence to sequence with attention. Here you want to produce French from English. And again, now what matters is bleu, but we're going to use Hamming as a proxy for sampling. And similar kind of result. So again, the baseline gives some kind of bleu, say 36.8. And when you play with tau, you get to a point where you get a slightly better result, 37.243. So a slightly less great result, but still working. And actually, every time we tried it, it works better. And it doesn't involve training longer or anything, unless it's very expensive to generate wrong sentences. But in our case, we use Hamming, so it was very efficient. So let me switch to a third topic, which is even more speculative now. So it's about order in the sequence-to-sequence framework. So it's again with colleagues in the brain team, and this was presented at iClear earlier this year. How am I doing on time? Okay. So let's go back to sequences. We've seen that there's so many places where you have sequences in problems, speech recognition, image captioning, etc. Sometimes the sequences are aligned, so for each input there's a corresponding output. Sometimes they are not, and when they are not, we use the famous now sequence-to-sequence framework. That's all good. I've already talked about it, but so that we know. There are zillions of places where in the last 2 years we've seen papers coming out about people using sequence-to-sequence to solve tasks like machine translation, captioning, speech recognition, parsing, dialogue, geometry, and this list is at least 1 year old, so there's even more after that. But what matters, what I want to emphasize here is that for all of these tasks, the way we represent the task is by having some form of representation of a joint probability. So, for instance, we have this joint probability of all the output sequence symbols, and we're represented as the product of each symbol given the previous ones. And if there are only 2 symbols, you have the joint probability of y1 and y2. Well, actually, there are at least there are 2 ways to represent this joint probability. You can say, well, it's the second one given the first times the first, or the first one given the second times the second. They are equivalent mathematically, but is there one that is actually better to represent than the other one? Both of them look the same here on paper. So let's try to formalize what we want. There are problems for which you want to represent the probability of a set of objects, a collection that is unordered. You don't have the order, or it's not clear what is the order, and you still want to maximize its probability. So you could say, well, forget about the order, forget about the relationship between the objects, let's just represent all of them separately. But of course, this would be crazy. You could also decide on one order, and that's what usually people do, and hope that this is the correct order. But maybe that's not good. So there are a few examples that we know of that likely there's an order and we don't know it. Like for instance, if you want to predict what is in an image and you know there are multiple things happening, knowing that, say, the first 3 boxes are cats gives you a lot of hint about what is the 4th one. So knowing what you've predicted should help you to predict the next thing. So, but maybe there's a better order. If you want to predict what are the actors in a movie, maybe it's better to predict first the main character and then the other ones, or maybe it's the other way around. We don't really know. If you want to maximize the likelihood of a set of random variables in a graphical model, should you first predict A and then D given A and then B given D, or maybe there's another way? It's not clear. In fact, even when for tasks for which the goal was to predict a sequence of words, like the man with a hat, a sentence, you can always take any sequence problem and transform it into a set problem by saying, I will represent the as the pair the one, and that's here. Man is now the pair man two. The second index represents where it is in the sentence. So I can represent it like this, and now I can reorder them, and it doesn't change anymore the meaning. That the second part here is the same as the first one. I've just transformed it into a way that lets me try to play with the order, and maybe there's a better order than just the obvious order. Maybe not. So let's look first at input data, and I want to first try to convince you that input order matters. So by what we have seen prior work of people playing with that without really understanding what was going on. So in machine translation, in the early machine translation work, where there was no attention mechanism, people have seen that if you want to predict from, say, from English to French, the best thing to do is to take the English sentence and reverse it. So input the English sentence reversed and try to predict the French sentence. When you do that, you gain some like 5 blue points. So there's a better order than the natural order. Same for another task called constituency parsing, where again, if you reverse the sentence, you get an improvement in F1 score. And there's many tasks like this where if you play with how you represent the input, just the order of the input, here you had to sort them in a way, here you had to reverse them, then you get better performance on how to predict the output. So the order of the input had some importance, but the problem is people have just tried in a random way and maybe they are better order. Or do we have like a way to optimize over these orders? And I think that was the point for that first part. So let me propose a simple algorithm to actually include this potentially complex ordering task for the input data inside the training algorithm. So we propose this read, process, and write algorithm, which looks as follows. You have some input data, x1 to xs, and normally you would read them with a recurrent net, one word at a time. But if you do that, then there's an order that is inherent, because when you read the second word, it goes on top of the state of the first one. So you're fixing the order when you do that. So now instead, we're going to just read them in memory and not use a recurrent net for that. They just go into memory flat, and then it's clear to see that now there's no difference between the order. You can actually put them in any order. They are all in memory. Now comes the process block. And this is going to be a recurrent net that will just look at the memory, pick one of the memory in a soft way, and add it to the state. And then go on, process again, go over the memory, pick one, and add it to the state. So one simple solution to that would be to pick the first, then the second, then the third, then the fourth. And if you do that, you get back to the normal recurrent net. But you can also decide to pick them in different order. Now, because all this is done in a soft way, you actually learn to do it, because you can use gradient descent. So you learn to read part of the memory before other part of the memory. And after a while, you're done, you have a state, and you can go on and write and whatever, process whatever you had to process. Another interesting point to mention about this way of processing data is that the number of loops you put in this process block is not necessarily related to the size of the input. So suppose you have 10 inputs. In the normal LSTM, you would actually read one after the other. So the amount of computation that you apply to your input data is exactly 10, or is a function of 10. But we could disconnect this and say, well, we're going to apply 15 computation time, even if the input was 10, because now the number of computation time is kept here in this process loop, which can be as big as you want. They are independent from the input. So this is not a novel idea. It was proposed also this year, concurrent to our idea, and by Alex Grave, and he calls this adaptive computation time, where in his case it's even more involving, because he's trying to predict how long we should process. Well, in our case, we fixed it to some number and we played with it. I'll skip the actual process, but this was well, I can quickly try to explain. I said that at every loop of process, we would select one of the memory and add it to the state. This is actually how it is done, and it's a soft way. So the way it's done, you have the memory here, and you have some process that tells you with some probability which of the memory I should use. So the probability of using the first slot given the state, the second slot given the state, etc. Someone gives me that, and with this probability, I'm computing an average memory, which is the weighted average of the current memory here, and that's what this thing is. Once I have the average memory, I can put it in the state, and with this state, go on and create a new probability over the next time I go on to look at the memory. So there's the loop that from the previous state, you compute where I should look again, and then give that as input to the model that says what I should look again. So these are all the equations that are needed to that. That's all I want to say about this. Now we tried a very toy experiment to verify that this was working. The toy experiment consisted of having n numbers, n random numbers, as input, and the task is to sort them. So you have to now output them in a sorted way. So this is you can use a simple model called pointer network to do that. A pointer network is a sequence-to-sequence model where the output is just a set of pointers to the input. So when your task is to produce something that is just a set of the input, like sorting, it's really you have a set of numbers and you need to output the same numbers but in a different order. Pointer network has been proposed last year as a way to do that, and it works very well. So this is our baseline, but we want to improve upon it. So what we did was doing these experiments over these sorting numbers where we varied how many numbers we want to sort, and also how much processing time we want to do. So N is the number of examples we want to sort. P is the number of loop in the process loop. Now we've also added one thing which we call glimpse, and glimpse is just one more processing time that we can do after every output. So for instance, we've processed P loops. Now it's time to output a number, or actually a pointer to the input. And now let's do one more processing time again, and then output a number, and one more processing time. And this is what we call glimpse. So we can or not use glimpse. And these are the results. So the numbers we see are out of sample accuracy, so new examples. And you get the point if you were able to sort everything properly, totally. So you don't get partial reward. You get it or you don't. So the higher the number, the better. So pointer network is the baseline. P equals 0 is like a pointer network without any knowledge of attention over the data. So this will obviously be the worst. Then you have with glimpse or without glimpse, and the number N here. So what we see is these numbers are the baseline. It's always better to have a glimpse. And as soon as you have at least one processing time, you get better result than the pointer net. And as you add processing times, you get better numbers. I mean, the numbers are... and what the other thing you see is that as N grows, the task becomes harder and harder, which is a known problem. But at least you get to be better in that very hard task. So this was a way to be able to handle data that has non-obvious input order. What about output? So suppose you have the task of producing the probability of a sequence of words. That's called language modeling. You can use a recurrent net to do that. So the question was, is it easier to represent words one after the other, or maybe you can change the order? So for instance, you could try to consider reversing the whole text and see if the likelihood changes. Turns out it doesn't change anything, because n-grams like this are the same as n-grams like that, so no difference. But if you try to represent your data in another way, here we tried what we called 3-word reversal. So you have all your words, and you switch them by pack of 3, and now you try to represent the data. So it's another ordering. When you do that, the performance degrades a lot. So perplexity is something that should go down, but with this word ordering, it has a bad impact on the performance. So there are word ordering that are better than others. Of course, here we kind of tried to find an ordering that was bad, and that's how we found this one. But it does mean that in some cases, it's important to find the right ordering. Here we tried another task which is called constituency parsing. Here, the goal is you are given a sentence in English, and you want to produce what we call a parse tree. It's a tree, and this is an example of a tree. So this is a sentence, and the parse tree says, well, there you have these tokens here, DT, NP, VBZ. This is the way to annotate the tree. Now, a tree is a tree, it's not a sequence, so you have to flatten the tree in a way that it looks like a sequence so that you can use sequence to produce trees. But there are many ways to flatten a tree. The two obvious ones are what we call depth first and breadth first. So these are two examples of ways you can use to flatten a tree. Both of them are valid, but maybe one of them is actually better to represent the tree than the other one. It turns out it is. So depth first is the best way to represent trees, at least for that task. But one needed to know about it. So again, these are tasks for which you can play with that and verify what's good. And it's okay when there's only 2 ordering, but if there's a combinatorial number of possible orderings, how do you know which one you should use? So we know that order matters, and that's important, so how can we handle that? So again, what we want is that the learning algorithm itself decides on what's the proper ordering. So instead of just trying to maximize the likelihood of your data for a fixed ordering that you hope is the best one, you are going to put the task of ordering inside the loop of training. So what you are going to do is ask the model. So now we're going to use the reinforced trick that Facebook was using for its paper that I talked about before. So we are going to ask the model to produce an ordering given the current input, and we are going to maximize the likelihood of this ordering. So there will be like two loops, one inside the other. One is maximize the likelihood of the data, but the other one is, okay, how should I represent the data? So let's try multiple orderings, pick the best one, and maximize according to the best one. And that's what these equations are. So how do we verify that this is actually working? Again, we tried the very toy problem. Here, the goal was to maximize the likelihood of a 5 gram, so a sequence of 5 words. What we did, again, was the same trick as I discussed at the beginning. I represent any 5 grams by a set of pairs of word positions. So the 5 gram, this is a 5 gram, can be represented as a set of this one is 2, 3, 5, 4, gram 5. And now you can see that now that I've done that, I can try to represent it in any order, and it's not clear what is the best one. So here's what we tried. We tried to train only on the what we call the natural ordering. So that is train with 1, 2, 3, 4, 5. So in the proper ordering. You can train a model with only examples of the proper ordering, or you can train a model with a fixed but completely different ordering. So randomly we picked 5, 1, 3, 4, 2. So what happens if you train with this ordering, 5, 1, 3, 4, 2, and you try to maximize the likelihood of all 5 grams with this order? That's interesting to verify what's going on. And now, so these are baseline in some sense. Now let's try to see, suppose we don't know the proper ordering. So we're going to try with only 2 possible ordering, this one and this one. We are going to train with examples of the 2 orderings and see if at the end we actually recover the maximum likelihood solution. Or we can try with all possible ordering. In this case, we just don't know what's the proper ordering. We're going to try all of them, and we'll let the model decide what's the proper ordering. So these are the results that we obtained. When we trained with the proper ordering, there was only 1 possible order, and it got this perplexity, 225. The lower, the better. If you try with the wrong ordering, there's still no order, but the perplexity is higher. That is, there is a better ordering, and you'd better have it, otherwise you're failing. If you train with 2 ordering, so you know that one of the 2 is correct, but you don't know which one, well, the model that I proposed recovers the proper ordering because it's able to go down to the same perplexity. Or if you consider all 5 factorial orderings, well, same, you recover the proper ordering. So there was an obvious ordering. It wasn't known. We trained with all possible ordering by having these 2 loops, one inside the other, and it was able to recover the ordering. So if there was in the data something, it was found by the model. Of course, these are toy problems. But that said, this brings me to the conclusion of this presentation. I think deep learning has been very successful, but there's a lot of work to do to improve on so many ways. I've tried to tell you today about problems in structured data, whether it's structure as input or structure as output. Sequence to sequence is a very successful way to represent sequences, or in that case, sets as well. There's plenty of approaches you can think of. We've been trying to add more knowledge of the reward function inside the training algorithm in a way that is still efficient. I've tried to show you that order matters, and there are ways to handle that. But clearly, there's a lot of research to be done in very many directions, And we're just at the beginning of the story, so I hope you will continue on that as well. That's it. Do we have time for questions?
Yes, we do. Okay. So if colleagues, if you have any questions, please lift up your hand and I'll get to you with a micro.
There's one here.
Hello, thanks for thanks for the talk. It was great. In the second part, where you mentioned the when you mentioned training translation model using the reinforcement method, you've provided an example how to sample from the reward for a particular kind of reward.
Yeah.
There are two stupid questions. First, the proposed kind of sampling, is it exactly equivalent to just basically augmenting data with generating sentences with a few words off, close to what you have in the originals?
It is a way to augment data, you're right, it is but it's a way to augment data in a targeted way. The way you augment data is through the reward function. So you're going to use your reward function to decide how you augment data. So if we tried, for instance, to augment data by just uniform sampling over these words, and that doesn't work as well, no. So putting the reward function into the way you sample new data was crucial.
And the second, I think even dumber kind of question is there a more or less constructive way to either, find an algorithm or to train such an algorithm that will sample from this reward for an arbitrary kind of reward function? Like the SIGGAN one?
No, arbitrary, I don't have any solution. But we do have solutions for some more than I thought, like the intersection over union, we have a solution. But I think it's going to be problem dependent. For each reward function, you need to think of a way to sample from it. Some might be more difficult than others. So there's no obvious way, maybe brute force, but that's not very efficient, to do it, as far as I know.
Is there a way to maybe learn such sampling in a more easier way than just learn a generative model?
Sure, everything can be learned. Let's try that.
Okay, and the last one, when you mentioned the, in the last part where it was about, basically differential data structures that were used there in generative models, do you still train them like end-to-end using only the final using only gradients on the outputs, or use any additional rewards to make training more efficient, since it's like end-to-end with?
Everything was trained end-to-end. I'm not sure where you think we were not using end-to-end. Like the order, I mean, for the output was using reinforce, but it's still end-to-end. The input was using plain attention, that was end-to-end. For the reward augmented maximum likelihood, it was end-to-end. So where did I not use end-to-end?
No, I was just doubting whether there is something maybe.
No, it's all end-to-end.
Yeah, thank you a lot.
As far as I know. Yes, there was.
Thanks for the talk. Actually, my main question has been already asked, but one more question I still have. So you're using reinforce algorithm for optimizing over this reordering.
I didn't use reinforce. Reinforce was used by Ranzato et al. But our approach does not use reinforce. It's using maximum likelihood. What we use is a trick to sample according to the reward function, but we train with maximum likelihood. While Ranzato et al. Was using sampling from the model and training with reinforce. So it's a very different approach. Mm-hmm. But we didn't like their approach, and that's why we went to this other approach. So we are not using reinforce in our reward augmented maximum likelihood. It's really maximum likelihood.
Great. Okay, thanks.
Any more questions? Don't be shy. I'm going to leave the country after.
Sorry for standing up again. Okay, so as for the problems with just direct reinforcement learning, and you mentioned the main one was that it's hard to obtain any reward if you are starting from random things. Yes. Is there I've heard in many other domains it was useful to train via actor-critic-like approach, where the network learns where to move from its current poor state to increase reward. Is there any constructive way to apply it in this particular problem?
Yeah, so for this Ranzato et al. Paper, what they do is they first try to train with maximum likelihood. So they first want to have a first model, and then they hope that sampling from it will give you information.
So, I mean, apart from pre-training, is there any way to maybe change the reinforcement learning algorithm but still train like by actively generating that mitigates this problem of...
Well, what we propose is a way to go around it by not sampling from the model, but sampling from the reward instead. Because now you control it, it doesn't change through time, you can actually sample prior to training, and you know the complexity of the task, and you control how bad it's going to be yourself. If you sample from the model, as most reinforcement learning approaches do, then yeah, you need a few tricks to do it properly with some scheduling, and it's hard.
Thank you a lot.
There was one here.
Thank you for your talk. Can you please explain again why we give wrong examples for model and train to give right sentences?
Repeat the question.
So you have mentioned that we are trying to teach our model wrong samples on
Yes.
on caption generations,
Yes.
And it gives right answer after
Yes.
this.
Why does it happen?
Yeah.
Okay, the reason it happens, I think, is even though we train with only wrong sentences, all the wrong sentences are sampled around the right one with some probability distribution that is centered at the right one. So you're going to once you're going to sample a mistake here, another time you're going to sample a mistake here, and you're like orbiting around the right thing. It's not biased.
And they're close enough to...
Yes, and actually close according to this tau that you can control, that says how much close you want to be. And tau is also a way to add some diversity exploration in your model. So I suppose that's why it works.
Thank you.
Still.
Thank you for your talk. My question is about this optimal tau parameter.
Yes.
Do you investigate the dependence of this optimal value on the language you use for the
No.
training?
We haven't, but it seems to be not sensitive enough because we tried two different tasks, translation and speech recognition, and the optimal tau was very similar, 0.85 and 0.9, and more importantly, around the optimal value, it was very flat. So it doesn't seem to be very important to have it right, exactly right, and it seems that from two different tasks, you get something very similar around this 0.8, 0.9 values. So I'm not saying it's always going to be good, but the fact that it is stable is a good sign, and that it's not too much task dependent. But we haven't explored more than that.
Okay, thank you.
Thank you very much. My question is, it looks very natural to change tau slowly during training.
While you train, yes. Yeah, many people suggested
Like
that
in simulated learning,
uh,
simulated annealing.
yes. We did not do it because we didn't want to do it, but clearly it would work better. Now, the reason we didn't do it is that there was a prior work which I worked on, which we called scheduled sampling, where there was this hyperparameter that you could tune with some schedule that would go down. And without going into details, if you found the right schedule, you would improve your performance on translation and speech recognition. But it was hard to find the right schedule. So the starting point of this work was to say no more scheduling. Just one hyperparameter that you tune once and for all and you don't touch it. It's much easier than having to fine-tune this scheduling problem. So I'm pretty sure it would work better with scheduling, but it becomes a nightmare to find a schedule. So that's why we didn't do it.
more questions? Yeah?
Thank you.
Hi.
About tau again, don't you think the tau parameter it can be different in different points of this multidimensional space?
Sure.
And maybe space is stretched and...
It could be, yeah. I mean, maybe there's a better way, a more complex way to represent this hyperparameter, but we did not explore it just because for simplicity only. So I think it might be the topic of another project.
Thank you.
Yes.
Yeah, okay, if there is no question, thank you so much, Sami.
Thank you very much for having me.
So guys, Seville is available for like 10 or 15 more minutes right here. If you have some personal questions or something, you can just reach him here and ask them. Thank you. Спасибо большое за визит.